Hi, this is Diego, and I'm gonna present you our experience in using machine learning and analytics tools to support network operation in remote communities deployment. Here is the content of the paper. First, we provide an overview of our commercial deployments in thousands of small communities in one country in Latin America. Then, we overview the challenges in managing such a large network operation in remote area cell sites. Third, from a dataset we collected from the operational network, we characterize the failures and the alarm pattern of these remote cell sites. Finally, we present an extension of the OSS to support machine learning and analytic tools to help network operations. We also show how machine learning and analytic tools can improve operations. In the paper, you can find all of this content, while in the talk, I'm going to mostly focus on the last two items. Our deployment is the one of the Internet para Todos project. The goal of this project is to provide sustainable mobile broadband to unconnected people in Latin America. The project is currently deployed in different countries, and in the paper and the talk we focus on one of them. The project is an infrastructure project that provides infrastructures to multiple mobile network operators who would like to provide connectivity in such area. It is based on open access technology and revenue sharing model, where the revenues are shared between the mobile network operator and the infrastructure provider. In the country we focus on, there are thousands of small communities deployed. Most of them are equipped with 2-3G connectivity, while some of them also have 4G involved. These communities are in remote areas, in the mountain, in the coast, and even in the rainforest. Actually, the average distance from the main road is 8 km, but some of these communities are tens of kilometers away from the main road. The cell sites deployed in these communities have different power supply depending on what is available. It can be solar panel, power grid, batteries, or a combination of those. The project leverages heterogeneous third-party backhaul network. It can be radio link, satellite, and fiber. Operation is managed from a centralized point. Whenever there is a problem to fix, operations try to fix it from remote first. When this is not possible, an on-field intervention is scheduled. In order to optimize and minimize the cost, the country is divided into 40 roads, and interventions in the same area are batched together. Here is an overview of how the network operation collects statistics from the network. As there are different vendors and different technology available on different sites, the statistics are slightly different. And also, the alarm collector has different ways to collect the statistics from the cell sites. The alarm collector also normalizes all of the statistics, so to have them all in the same form and clean their field. After that, all of the alarms are stored in the alarm backend in the same format. Alarms can be in two states, either active or clear. On the top of the alarm backend, different applications can be built. There are monitoring dashboards giving the status of the network, diagnostic dashboards providing insights on potential failure and potential solution to the failure. There is also a rural bot to interact with the on-field team to tell us which is the next site they have to go for an intervention, what is the status of a given site, and many other insights. Also, there is the decision engine, that is where machine learning and analytics tool can be built to improve the OSS application. I'm gonna show you later on one of the applications that we developed. We collected 5 months from our operational network, and I'm gonna present some analysis of this data now. For these 5 months, we have about 6 million of alarms of 46 types. 4 to 5% of these alarms are actually failure, meaning that these cell sites do not work. There are 3 main types of failure that are present in our dataset. The most common one, being an order of magnitude more present than all the others, is the GSML cell out of service. This can be a temporal outage due, for instance, to a misconfiguration, or it can be a more permanent one, like a manual blockage of the cell site. Another fairly common failure is the lack of power supply, and the actual problem might depend on the power supply configuration of the site. It can be a problem with a battery or an outage in the power grid. Another failure, which is less present in our dataset, is a problem with a data loss at the antenna port, and in this case the cell site has been turned off to avoid damaging the equipment. Here is a deeper analysis of the data. On the left-hand side, we analyze the duration of the alarms and the failure, also distinguishing between major alarms and minor alarms. The first thing you notice is that the failures are usually longer than the alarms. Nevertheless, the failures are short. 90% of them are shorter than 1 hour, and only 1% of them is longer than 24 hours. On the right-hand side, we analyze the inter-failure time. We observe that for most failure, the inter-failure time is less than 1 hour. So this basically shows that most failures are temporal and flat. Actually, from an operational perspective, the operation team considers a failure being continuous if the time between two failures is less than 1 hour. These temporal and flapping failures are mostly due to vehicle saturation or battery outage. Nevertheless, for this temporal failure, it is not worth scheduling intervention because the time the technician is going to be on the site, the failure has already been solved. Therefore, this clearly highlights the need of control and predictive mechanism to avoid this costly and unnecessary intervention on a site. Also, it is important to understand what is the nature of the failure, to equip the operation team with the right tools to fix the issue, because it's not possible to carry tools and material to solve all the potential issues that the intervention team could find on the site. Now here we analyze what is the distribution of the number of alarm and failure across days and across sites. The first thing that we observe is that failures and alarms are mostly concentrated during daytime, when the network is more used. Actually, alarms are mostly concentrated in the afternoon and in the evening, when there is even more traffic in the network. All of this highlights that the network patterns are correlated with the failure patterns. And so one of the main causes of the issue is the high load on the network. This is something that I was already mentioning earlier, that very often there are issues with network congestion or vehicle saturation. Also, you see that some sites are more affected than others by alarms and failure, and this depends on their load and on the connectivity they have. Now, let me talk about one of the applications that we built for the decision engine. As I mentioned earlier, there are many failures that are temporary, for which it is not worth to schedule an intervention, because the time the technician is going to go on site, the failure has already been solved. From an operational perspective, we define a failure to be permanent if it is longer than 24 hours. So the problem here is to detect this permanent failure out of all the failures present in a system. We use machine learning tools to solve this problem. From a machine learning perspective, this is a binary classification problem. It is a very unbalanced problem because only 1% of the failure is actually permanent, meaning longer than 24 hours. For this problem, we also have ground truth for the failures that happened in the past, for which we already know if it's been permanent or not. To solve the problem, we use XGBoost, which is a powerful machine learning technique. We also experimented with other tools, and especially with deep learning techniques. Nevertheless, for this specific problem and this specific dataset, we could not see any benefit in using this most advanced technique. As input feature for our problem, we use mostly the alarm, and more specifically statistic computed in the alarm over past time windows. Example of statistic can be the number of times an alarm appeared, how long it was, what was the total duration of the alarm over the past time window. In addition, we use other information about the cell size. For instance, its location, how it is equipped, how many users. We also use other information like the weather, the time at which the failure happened. As output, we tune the model to tell us if a failure is permanent or not. After 6 hours it has been active, 12 hours it has been active, or 18 hours it has been active. Here, we analyze the precision recall provided by the model in identify permanent failure. So this is the precision recall only on the permanent failure class. Every point in the plot corresponds to a different value of the classification threshold, which is the threshold used by the model to discriminate between permanent and non-permanent failure. In the plot, we report results for evaluation at 6 hours, at 12 hours, or 80 hours for an active failure. We also report different values for the compensation for the class imbalance, which is a compensation that is used to try to solve the imbalances of the problem in XGBoost. First thing to notice is that there is a clear trade-off between the precision and the recall. So the higher the classification threshold is, the more we are precise identifying permanent failure, but the less of this failure we identify. Also, we observe that the class imbalance parameter does not really help in solving the issue. However, precision and recall does not really tell us how this helps operation. For this, we define a cost model and compare it with respect to a baseline. The baseline is the cost of waiting 24 hours. The cost model depends on two main factors. On the one hand, there is the revenue loss in having a cell sits down. This depends on the number of users and the revenues of that site, the presence of competitors, and other parameters. The versus cost depends on the location of the cell sites. We could not use, for confidentiality reasons, values from our operation. Therefore, we vary the ratio between the revenue loss and intervention cost, and we plot here what are the cost savings provided by our model with respect to the baseline scenario. We also plot different values of the compensation parameter. First, we observe that if the ratio is lower than 0.4, there is no point in using the model, because there is no gain with respect to the baseline scenario. From that on, we see that the cost saving increases and can reach up to 20% when the ratio between the revenue loss and the intervention cost is 10. Again, worth noticing that the compensation parameter does not really provide any benefit, that the compensation parameter equal to 1, meaning no compensation, is actually a good choice. Here we also lie to extreme cost scenario that we're going to use next in the evaluation, when the ratio is 0.1 and when the ratio is 10. Again, depending on the cell site and of its value and intervention cost for that site, the operation can decide or not to use the model. Now, we compare our model to some baseline. First, we use a random baseline, which is a vanilla baseline, which decides randomly if a failure is going to be permanent or not. Then we use two other baselines that actually we define after using the model and analytic techniques. One is deterministically consider all failure as permanent after 18 hours, and the other one is to probabilistically select a failure to be permanent or not proportionally to its duration. First of all, we observe that the Foukas scenario 1, the model outperformed all the heuristic, even the one we derived after using the model. Actually, the heuristic provide a negative gain with respect to the baseline scenario, meaning that they are more costly, and the model provide up to 5% gains. Also worth noticing that after 6 hours and 12 hours failure has been active, there is no point in using the model because it doesn't provide any benefit, while the heuristic provides significant losses. In the cost scenario 2, we observe that benefits of the model are limited with respect to the heuristic we define after running the model and after doing analytics. With respect to the vanilla baseline, though, the model provides important gain up to 10%. So here is important to notice that using these analytics and machine learning could also help providing heuristics that are simpler to deploy and still provide the same benefits under some cost scenario. It is also important to notice that there might be still some benefits in using the model after 12 hours a failure has been active, but this is the same gain as waiting 18 hours, while at 6 hours the benefits are low. Another thing that is not shown here is that there is a high variability across months. For instance, if we take the cost 1 scenario, the maximum saving can be achieved is up to 12%. But it is a high standard deviation. This high variability is due to several factors. There are many failures that are unpredictable and vary significantly across months, as well as the number of users and the usage of the network, and this explains the variability. There are more insights which you can find details in the paper. I'm going to list here some of them. As you probably already guessed, the most relevant feature of the model is the failure duration, so how long the failure has already lasted, which is account 12% in the decision process. And this is what actually drove us to define the proportional heuristic that I mentioned earlier. There are other important features that accounts for about 2% in the decision process of the model, and I'm listing here the ones that account for about 2%. There are 130 more that account for less than 1%, and therefore they are not really critical. Another important information from an operational perspective is how often do we have to train the model. And it turns out that the model needs to be trained every month. If it's training more often, there is no benefit. If it's trained less often, then we have a loss in the performance of the model. Another important information is how much past data do we have, how many failures we used for in the past. Turns out that the best value is again 1 month. Less than that is probably not enough for the model to learn. More than that, the model still provides less benefit. And the reason is that the user changes over time and their key infrastructure always evolves. Therefore, it's actually counterproductive to use more data than 1 month. This is something that has also been shown already in the previous work. Also, when considering a single alarm to perform the statistic as an input feature, we consider 24 last hour. We try with different parameters and considering more time or less time would actually not be beneficial. Here are the main lessons learned from this work. First of all, we believe that the experience of internet para todos can be beneficial to the design and the management of future remote community deployments, in this case specifically for the management. One important aspect is trying to use a data-driven approach to understand the status of the network, the failure, and how the field team operate to limit the cost, because cost is one of the main issues in this remote community deployment. Another important outcome of the work is that failures are mostly temporary, caused by power outage and congestion issues. This tells us that we need control and predictive mechanism to schedule intervention, and that's actually something that we have been showing in the work. And second, it can clearly indicate some of the main causes, so helping the operation team either to identify long-term fixes or to provide the operation team with the proper tools that make the on-field intervention. Also, following the data-driven approach, we highlighted that machine learning analytics can actually help to reduce costs in the area or in general to improve the performance of the application used by the operation. Thank you very much.